Good morning, everybody.
Good morning.
Today we are going to be talking through chapter 13. We're going to start out with some nomenclature. Chapter 13 is all about ethers and epoxides. In terms of nomenclature, we're just going to do the ethers. So there's a couple of different ways you can name ethers. You can either name them as simple ethers. So, for instance, this here, we're just going to identify the two halves of our ether here. So on the left side here, we would call this a propyl group. There's 3 carbons to it. On the right side, we call this an ethyl group, 2 carbons to it. Putting them together in alphabetical order, you'd call this ethyl propyl ether. So basically, anytime you have 2 simple groups coming off of it, that's how you treat it. Another example, we have a methyl and an ethyl here. You're putting them in alphabetical order, so you'd name this as ethyl methyl ether. If you had 2 ethyls here, you would call this it'd be just diethyl ether. The other option for these is if it is a substituent on a much more complicated molecule. So let's say we have something like this here. We're not going to try to identify we're not going to try to ethyl and then whatever this is. We're just going to treat it like a normal molecule. And then when it comes to this group here, we would refer to this as an ethoxy group because there's 2 carbons on there. So F because of the 2 carbons on here, and then oxy to indicate that it's an ether. As opposed to if we had this, we would refer to this as a methoxy group because now we only have 1 carbon. And over here, if we had 3 carbons, this would be a propoxy group. Well, let's actually name the first one. So looking, I'm gonna add an extra carbon. Nope. At this compound here, I'm probably gonna number it from right to left. So 1, 2, 3, 4, 5, 6, 7. In terms of priority groups, this doesn't rank very high. It actually ranks with like halogens. So our number 1 priority is still alcohols. And this is in our lowest priority group with halogens. Ethers and carbons here. So it doesn't really make much of a difference. We're just kind of trying to get our lowest amount of substituents still. So we've got 7 carbons. This would be a heptane. On 3, we have an ethoxy. On 4, we have a chloro. If I'm doing RNS, I've got an oxygen, so that's going to be our highest priority. So 1 where the oxygen is, 2 on the chlorine side, 3 on the ethyl side here. This is going counterclockwise. This is going to be S. Over where our Cl is, chlorine, carbon bond to oxygen, carbon by itself, also going counterclockwise, also S. We'd refer to this as a parentheses 3S, oh God, 4S. Putting things in alphabetical order, so C comes before E, 4 chloro, 3 ethoxy, heptane. And just to kind of hammer home the priority thing, because these are kind of very low in priority, we had a molecule like this here. We're going to be going through our alcohol first. And just treating this like it's a normal chlorine or something. We don't really care that much about it. So we had this molecule down here. We would number this 1, 2, 3, 4, 5, 6, 7, 8. We would refer to this as a 7. We've got a propyl group here. So 7 propoxy. To octanol. Okay, so that is our nomenclature. We're never gonna use the oxygen as like part of our counting. It's always gonna be the longest carbon chain. So you'll never do something like 7, 8, 9, 10, 11, where you'll use the ether. You'll always just kind of treat it like it's one giant substituent. So you're kind of treating this like it's the equivalent of like a big chlorine or something like that. Does that make sense? Okay, cool. We're going to move into some reactions. So our simplest reactions, we're going to start on work 13.5. We're going to talk about Williamson ether synthesis. Which is really a very straightforward thing. So if we take an alcohol, like ethanol here, and we throw in sodium hydride to act as a base. Oh, wow. There we go. So sodium hydride to act as a base here. We can pull off this proton to generate an O minus here. And then from this point, throw in a alkyl halide. Let's do a bromine like this ethyl bromide here. And we can do an SN2. So we're going to attack at this carbon center, kick out this Br, and we'll make diethyl ether here. So really straightforward. I mean, we've talked about this basically in the past, just maybe not ever actually highlighting it. If you deprotonate an alcohol and throw it in solution with an alkyl halide, you can generate an ether. Okay, some different ways to generate ethers. Besides this, we can use a reaction that we learned in chapter 8. So if we take mercury acetate as well as a double bond here, so an alkene. So back in chapter 8, we learned that if we added this mercury acetate in solution, I'll draw the mercury acetate. This had the ability to attack, kick out one of these acetates. And then from here, our mercury is going to cyclize to make a 3-membered ring. From this point, our other reagent was always water. So water would come in. Attack at this more substituted position. Kick out our mercury. We do an SN2. I'm going to lose a proton. And then sodium borohydride can come in. And give us an alcohol here. Okay, so what we didn't really talk about was that this water here can be interchanged with an alcohol, and we can use this to make an ether. Let me give you guys a second to get caught up on writing this, and then we'll kind of go through this again and swap out this water for an alcohol and show how this can make an ether pretty simply. Okay, so looking at the same molecule, if we now use, in this case, let's say ethanol here instead of water, our first steps are going to be the same. So we're going to we can walk through it. Attack this mercury. I think I drew this going up before. We can cyclize. And then from this point, instead of water coming in, we can have ethanol come in. It is going to do an attack at this more substituted position. And then our sodium borohydride can reduce off that mercury. To give us an ether here. Okay, so this is a nice way to make ethers from alkenes. It's kind of a review just to kind of put these two together. If I add in mercury acetate, with water here, versus if I do it with ethanol. Instead of having an H on there, I'm now going to have an ethyl group. And then if I want to do something with much larger, I don't know, let's take this alcohol. We're just following the same concept we've been doing. Oxygen's going to be coming off of this more substitute position of our double bond. Let's see. And then we can add whatever size ether we want to add. Okay. The next thing we're going to talk about is how to break them down. So if I have an ether, and I throw in HBr and heat, this is going to fall apart into three different components. So we're going to end up breaking the bond on both sides of the ether. We're going to generate alkyl bromides. You could also do this with HCl, as well as water. So these are kind of the three components. This is how they break down. Let's talk through a mechanism for how this happens. So when we have HBr in solution with this ether here, we are going to protonate our alcohol, or not protonate our ether. From this point, we have a really good leaving group. It's not very specific as to which side of this happens first. I'm just going to draw it happening on the left side first. It could just as easily attack on the right side. So I'm going to draw it attacking here. But it could have attacked on the ethyl side. There's no reason why it would happen on one or the other. One versus the other. So that would make our bromo here plus ethanol. We are still in HBr, so we can still pick up another proton. And then BR can come in and attack this one. This is going to give us this alkyl halide. We already have this one. And then our byproduct for this reaction is water here. Give you guys a second to write this down. So to summarize, we have, let's see, I don't know. Let's do this odd looking ether here. We threw an HBr. We're going to break both halves of this down. We'll get a BR on one side. We'll actually get BR on both sides. So we would get this plus water in solution. So this works for sp3 centers. If we start having sp2 centers on one side, for instance, this benzyl alkyl ether or phenylethyl ether, if we add an HBr and heat, this is going to change things just a little bit. So we're still going to pick up a proton. Because SN2 reactions only really happen at sp3 centers, our BR is going to selectively attack here. And at this point, our reactions need to stop. These phenyl groups have a lot of resonance into their ring. And this is going to prevent this alcohol from picking up another proton. So this is effectively going to stop this reaction. And this is just going to be our product. We're only going to break this on the sp3 side. Our sp2 center to that aromatic ring is going to remain as is. So pretty straightforward alternative. If you have this like an aromatic ring on one side, it's only going to break your bond on your sp3 center. If you had two aromatic rings, this is just going to give you no reaction. All right, so we are going to do a little bit of epoxide formation and then take a break. So you guys already know one way to make epoxides. So a long time ago, we learned MCPBA and H3O plus. This is back in chapter 8. Lets us make alcohols that are anti to each other. If we just add in the MCPBA, we were able to stop at just this first step where you generate an epoxide here. And then from here, we've always added in water. There's or H3O plus, there's a whole different amount of reactions that we can add in instead of this that we'll talk about in a little bit. But if you just add in your MCPBA, you're able to stop this at our epoxide. So MCPBA is a peroxy acid. It looks something like, well, looks exactly like. This here, the key, whoops, no, I have an extra carbon. Component of this being this kind of peroxide slash carboxylic acid here. This is going to interact with a double bond. It's going to do a lot of weird arrow pushing. I'm not going to make you guys memorize this particular arrow pushing pattern, but just know that MCPBA will give you peroxide in solution. You could also do this with just any general peroxy acid, so it didn't necessarily have to be MCPBA. That just tends to be the one that we use a lot because it's a cheap reagent. Okay, another way to make epoxides is going to be through basically that Williamson ether synthesis we talked about earlier. So if you remember, we took an alcohol, added in NaH, and some sort of alkyl halide. This let us deprotonate. And attack here. We can use this same principle. We're going to use a reaction we again learned from chapter 8. So throwing in Br2 and water is going to let us brominate. I'm not going to go through this whole mechanism. You guys should know this one already. This is just going to give us, let's see, anti-addition of alcohol and bromine. So using the same concepts we did before, if we throw in a base, the book usually uses NaOH, but really you could use a bunch of different ones. You can deprotonate your alcohol. From here, we are nicely set up to do a Williamson ether synthesis. So this can come in, attack here, kick out this BR. And make an epoxide. All right, so a little bit of review. We throw in MCPVA with this alkene here. Oh, that's just the same thing. This lets us generate an epoxide. Alternatively, BO2 and water, followed by base. Lets us also generate an epoxide. Okay, this is kind of a natural stopping point or breaking point. So we're going to take about a 10-minute break and meet back here at 10:04, where we're going to talk through the rest of this chapter. So I will see you guys in about 10 minutes. All right, I'm going to give you guys about 5 minutes to work through these problems. Once we're done with them, we will move on to the rest of the chapter. So meet back here about 10:10, and then we will go through these. Let's say 10:09. I don't think it'll take you that long. All right, so we are first one here. We're making ethers. Gonna pull off our proton. I'm gonna kind of draw this all in one step. Lose this guy. Attack here. So we still have our original alcohol. We can start by drawing that. We've now made a bond to this 2 carbons followed by an isopropyl, and should give us this ether here. For our next one, we are doing, it's a normal Markovnikov addition. If we take a look at our double bond, we got a primary and a secondary. It's going to add an alcohol to our secondary center. And then our alcohol should have a carbon followed by this isopropyl here. In HBr, this is going to degrade. There are sp3 on both sides of this, so it's going to end up completely falling apart. To give us a bromine on both sides of this plus water. Versus in this last example where we have an sp2 on one side, so this is sp3. This phenyl ring here is sp2, so it's only going to break apart in the sp3 center. Oh, we're in HCl this time, so it's going to chlorinate to go with this product. Hopefully fairly straightforward reactions. Are there any questions about these? Okay, so we're going to talk about, let's quickly do thioethers. It'll take, I don't know, a couple of seconds. And then we'll do epoxides after that. So thioethers, I don't even know why this gets its own section. Essentially, anything you can do with carbon, you can do with sulfur also. So if we added an NaSH, so if I did this with NaOH first, I can make an alcohol, throwing in NaH, followed by, I don't know, ethyl chloride here. Lets us make this ether. We threw in the thiol version of this. We can do the exact same reaction. So you can make this thiol and then throwing in NaH and HCl. Let's make a thiol ether. Pretty much anything you can do with oxygen, you can do with sulfur also. And they're basically just interchangeable in this way. So I'm not going to go through a ton of reactions that deal with them, but just know that sulfur is basically an oxygen replacement. If you can do it with oxygen, you can do it with sulfur. All right, let's talk about epoxide openings. If I take MCPBA with an alkene, there are two different things that I can have happen. We're either going to go down a base catalyzed pathway. I'm going to say base / nucleophile because they're not really base. Or we can do what we normally do, which is our acid catalyzed pathway. And this is what we think of when we had something like, for instance, H3O plus. So our MCPBA and H3O plus always leads us to the anti-alcohols. But we're going to start with this base catalyzed one. So for this, we're not going to protonate. Let's actually, let's delete this. If I just take this epoxide as is, I throw in a nucleophile. it'll attack on the less substituted position. We'll pick up a proton from somewhere. To generate this alcohol. Alternatively, in acid, because we now have this positive charge, the positive charge is going to be shared with the more substituted center of the epoxide. So it's going to be shared with this tertiary center. And when we add in a nucleophile at this point, it's going to open our epoxide on the other side. And we'll do a bunch of actual examples in a second, just to kind of give you a concept of what's going to happen when we have acid. We're going to be opening on the more substituted center. When we don't have any acid, we're going to be opening on this less substituted center. So let's do a specific example. So we have our epoxide. If we throw in sodium ethoxide, we think way back to when we were doing SN1 and SN2, you would call this aprotic. There's no proton versus if we had something like ethanol, now we have that proton on there, we call this protic. So we're in our aprotic version up on the top here. So we're not going to protonate this epoxide at all. We are just going to have, oops, wrong button. Our electrons come in, they're going to come and attack at our less substituted position. We're going to, well, we would flip our stereochemistry, but in this case, it's just going to make a achiral center. Because there's two hydrogens on there already. And our last step, we add in water, which gives us an H plus to pick up. And give us this product. So if we're looking at this from like an analytical standpoint, our epoxide is connected to two different centers. One of them is primary. One of them here is tertiary. We're in an aprotic solution. So we're going to come in and attack at that primary center. That's where our nucleophile is going to be coming off of. And then our oxygen remains attached to that tertiary center. There are a whole bunch of different reagents that we can do this with, and they're all going to have this exact same pattern. So let's take a look at a couple of them in a row, and then I'll break down. Actually, I'm going to write them all out, and then we'll break down just a few of them. So yep. So from this oxygen here, the one that we just talked about, throwing in Na and then an ether or an alcohol. Let's just generate this ether alcohol here. If we add in something that is really just a strong nucleophile like NaCN, they're all going to do the exact same thing. So it's going to attack. At this more substituted position, we're going to generate what looks almost identical. I'll draw my CN in blue. Oh my God. We're adding CN to this primary position. Another one we can do, so anything we do with oxygen, we can do with sulfur, Na, thioether. Make it propyl this time. So we're going to attack at that primary center. Adding sulfur, and in this case, it's 3 carbons. Some other ones we can do is if we add in LAH. And water here, so our hydride is going to be what's opening this. And then alternatively, we could also use a Grignard. to add carbons to our chain this way. So all of these are adding at this primary center. Everything is, you can say it's all neutral. There's pretty much either sodium as a counterion for all of these, some sort of magnesium bromide, or this lithium from this lithium aluminum hydride. They all have some sort of counterion to them. They're going to just act as nucleophiles. They're just going to come in, attack at this less substituted center, and open your ring. So let's go back to that first example. We're in Na. So sodium methoxide, second reagent is water here. We're going to come in our less substituted position. To make this ethoxide, ethoxy alcohol here. If we instead exchange out this aprotic sodium methoxide for something like H plus and ethanol here, this is going to change our selectivity. So when we add an H plus, we're going to immediately protonate this epoxide. And once we do, this unstable molecule immediately becomes even more unstable. So the way it's going to orient itself to try to distribute this charge is it's going to try to put it mostly on this tertiary center. So it'll do something that looks like, just kind of like an equals. It'll lengthen this bond here to weaken it. It's going to put most of this charge on this tertiary center, because that's the one that's easier to handle the charge. So because of that, now our water is going to want to attack at the other side. Or not our water, our ethanol. So ethanol is going to come in and instead attack here. We'll still open our epoxide. Now we're opening it on the less substituted center, or sorry, the more substituted center. Giving us this opposite ether alcohol situation. So on our aprotic example, we ended up with the ether on our primary position, the alcohol on our tertiary. For this protic example, we ended up with the alcohol on our primary and the ether on our tertiary. And there's a bunch of different reactions you could do when you're looking at these, just like the other one. Let me give you guys a second to get caught up on writing. So taking a look at our epoxide, throwing in H plus, and let's say, whoops, there we go. Propanol here. We're now going to be opening on our more substituted position. Similarly, we could add in water, which is the reaction that we've talked about forever. So H3O plus. This lets us create our diols like we've always done. Other options, we could add in something like HBr, HCl. And this will let us brominate. So opposite concept as last time. Now that we're in these product solutions, we're able to go from, or we're going to add to our more substituted position as opposed to our less substituted position. So some interesting reactions you can do. Kind of going back to our epoxide opening or generating our epoxide. So when we added HBr and water, nope, Br2 and water. We generated our alcohol in our more substituted position, Br in our less, throwing in base, let's make an epoxide. And then from here, if we wanted to flip it, so currently we're on the secondary and the tertiary, throwing in something like HBr. Is going to let us make the opposite. Really bad. Alcohol and bromine prop. Oof. So now we have this bromine in our tertiary and this alcohol in our second. So this lets us do a little bit more control of things. We can kind of switch up some positioning that we weren't able to do previously. All right, so a little bit of a review, and then we're going to get out of here early today. And I might talk through a few of these that I didn't really talk through before. So I'm going to add a couple more to this. We have two different epoxide opening possibilities. Our aprotic one is going to be where we're adding in things like Na ethoxide here. These could be opening in a less substituted position. We can do this with water. We didn't really talk about this. So this would be NaOH. Going to still give us the same answer. We can do NaCl. NaCN. A thiol ether, so NaS. We could do a Grignard. Putting these three carbons here. Or we could do LAH. All of these are aprotic. They're all adding to this less substituted end of our epoxide. I'll box this out a little bit. Alternatively, for our protic reactions, so for instance, HBr, we're going to be adding to this more substituted position. H3O plus isn't really going to give us a different answer than NaOH. I guess we're just adding diols. But if you make it into an ether or a thioether, so let's do the ether. We'll be adding to this more substituted position. So now all of these are adding at this tertiary position. And they all have H plus. H3O plus can be rewritten as H plus and H2O. And then HBr here, or H plus and Br minus. All right, so that is epoxide opening, and that is the end of chapter 13. So I'm going to stop here for today. We will pick up with chapter 16 tomorrow, which is the last chapter that's covered for this exam. We'll spend about 2 days talking through it because it's a little bit more complicated. This one is just kind of rinse and repeating things that you guys have learned a long time ago. These are going to be some absolute brand new reactions tomorrow. So I will see you guys in recitation, I believe, for the... Oh yeah, someone asked if you need plus minus enantiomers for when you use stereochemistry. If your product gives you, so a lot of these are achiral because we have 2 protons here. But if you do end up with something that is chiral, you will need to indicate your stereochemistry on these. All right, so I will see you guys either in recitation if you're in the 12:05 one today, or I will see you guys on Friday.